When you think about the basic building blocks of our world, all the elements, they pretty much fall into two big families. You've got your metals and your nonmetals. But the line that divides them, oh, it's way more interesting than just shiny versus dull. So what really truly sets them apart? To really get a handle on just how different these families are, check this out. Take a single gram of gold, that's about the weight of a paperclip. You could draw that out into a wire that stretches for 2 kilometers. That's just wild, right? And that one incredible property gets right to the heart of what makes a metal, well, a metal. Okay, but now imagine trying that with something like a piece of coal, which is mostly carbon, or a chunk of sulfur. What happens? It just crumbles into dust. So it really begs the question, what's going on at the elemental level that makes them act so completely differently?
To answer that, we're going to start by looking at the most obvious clues nature gives us, the ones that make up this elemental divide. We're talking about their physical properties.
Yeah, the most direct clues are always the physical ones. Before we even get into the deep chemistry, we can learn so much just by using our senses. What we can see, what we can touch, and believe it or not, even what we can hear.
So let's have a little fun with this and frame it as a face-off. Team metal versus team non-metal. We're going to compare their key characteristics side by side to see how they really stack up.
First up in the ring, malleability. Now, this is just a fancy word for the ability to be hammered into super thin sheets without breaking. And in this category, gold and silver are the absolute undisputed champions. Just think about gold leaf. It gets hammered so thin that it's practically transparent. And this brings us right back to that mind-blowing fact we started with. That ability to be stretched into a thin wire, that's called ductility. And gold is the most ductile metal we know of, which is exactly why it's so crucial for all that microscopic wiring inside our high-end electronics. So, when you put them head-to-head, the classic differences are crystal clear. Metals are typically lustrous, shiny, malleable, and they're fantastic conductors of both heat and electricity. They're even sonorous, which means they make a ringing sound when you strike them. Nonmetals, on the other hand, are pretty much the exact opposite. Dull, brittle, and really poor conductors. But here's where it gets interesting, because nature loves to break its own rules. You've got metals like mercury that are actually liquid at room temperature. You have nonmetals like iodine that are shiny, or graphite, a form of carbon that can conduct electricity. These exceptions are a huge clue that physical properties alone don't tell the whole story. To really get it, we've got to go deeper. You see, the real dividing line, it's all about the chemistry. To see the true personality of these elements, we have to see how they react, how they interact with other elements. And believe me, the differences in reactivity can be dramatic. You drop a tiny piece of sodium in water, and you get a fiery explosion. But drop a silver coin in that same water, and, well, nothing. Absolutely nothing happens. They're both metals, right? So what on earth explains that massive difference? Well, the answer lies right here, in what's called the reactivity series. Think of this as the ultimate power ranking for metals. At the very top, you've got the super reactive ones like potassium, and as you go down the list, their reactivity decreases, all the way to the least reactive, like gold, at the very bottom. This simple chart is the chemical playbook that tells us exactly which metals are going to go wild and which ones are going to be stable. So, we've seen how metals behave among themselves, but what happens when a metal comes face-to-face with a nonmetal? Well, it turns out it's less of a face-off and more of a classic case of opposites attract. And the driving force behind all these reactions is a single, universal goal in chemistry: stability. All an element really wants is to have a completely full outer shell of electrons, just like the superstable noble gases. Metals and nonmetals just have totally different strategies for getting there. Let's watch this in action with a perfect example: making regular table salt. Sodium, our metal, has one extra electron in its outer shell that it is just dying to get rid of. And chlorine, our nonmetal, is just one electron short of having a full shell. It's a perfect match. So sodium transfers its electron over to chlorine. This makes the sodium positively charged and the chlorine negatively charged. And, opposites attract. They snap together and form a super strong ionic bond. And the result of this special bond is something called an ionic compound, which has its own unique set of properties.
Table salt, for instance, is a hard solid with a really high melting point. But here's a cool twist. As a solid crystal, it won't conduct electricity at all. But if you melt it or dissolve it in water, those ions are suddenly free to move around, and that flow of charge turns it into an excellent conductor. Okay, so we're getting the chemistry. But how do we actually apply this knowledge in the real world? How do we get these vital metals out of rocks in the ground and turn them into the materials that build our entire world? Well, the answer lies in a field called metallurgy. It's the science and art of taking rocks from the Earth's crust, we call those ores, and using chemistry to unlock and extract the pure metals trapped inside. And it's a whole journey to get from a rock to a refined metal. Of course, it starts with mining the ore. Then that ore has to be enriched to get rid of all the useless stuff like sand and dirt. Then comes the crucial third step, using chemical reactions, often guided by that reactivity series we saw, to finally extract the metal. And lastly, it's purified into its final usable form. And some of these chemical reactions are just incredibly powerful. Take the thermite reaction, for example. In this reaction, a more reactive metal, aluminum, literally rips the oxygen away from iron oxide. It's so intense that it produces molten iron right there on the spot, hot enough to be used to weld massive railway tracks together. It's applied chemistry at its absolute most spectacular. But pure metals aren't always what we're after. A lot of the time, we can create even better, more useful materials by making alloys. An alloy is just a mix of a metal with other elements, specifically designed to give it better properties, like making it stronger, harder, or resistant to rust. And this is the perfect illustration. Pure iron, all by itself, is actually surprisingly soft. But if you mix in just a tiny bit of carbon, a non-metal, suddenly you get steel, a material that's hard and strong enough to build skyscrapers. It's just a brilliant example of how a metal and a non-metal can team up to create something way better. And it turns out we've been mastering the art of alloys for a very long time. A truly stunning example is the iron pillar of Delhi. It was forged over 1,600 years ago, and this massive 6-ton pillar has been standing out in the open, famously resisting rust that whole time. It's an incredible feat of ancient metallurgy that still baffles scientists today. And this really leaves us with a fascinating question to chew on. Today, we use all our advanced science to create rust-resistant alloys like stainless steel. So how in the world did ancient metallurgists 1,600 years ago manage to create a massive iron pillar with such amazing longevity? It's a powerful reminder that the story of metals and nonmetals, well, it's a story we're still uncovering.